And so as the clock strikes 10 o'clock, it gives me great pleasure to welcome you all to another Question Time Extra Time, our series of webinars when we delve deeper into issues around F gases, refrigerants, and all things in between. This session, I'm very excited to be introducing the subject of heat pumps and heat recovery, thanks to our friends at Chemours. So over the next hour or so, we will be having a look at all the opportunities available with low GWP refrigerant, and there are quite a lot of them. So I'm not going to spend too much time. Just a little bit of housekeeping for you. This is a question time event, and so that means we need questions from you, the audience. You can do that by filling the Q&A box in. Little tip is don't press the return bar or you'll be sending us 6 questions at a time. Don't use the chat function, please, for questions. Just use the Q&A, and we will be asking those questions at the end of the session. And so the way it's going to work is we'll have 3 colleagues from Chemours to give you the benefit of their wisdom in the various areas. So we'll be hearing about an overview, we'll be hearing about heat recovery, then we'll be hearing about heat pumps, and then we'll all come together and discuss your questions, our questions, everybody's questions. So without further ado, the catchphrase of question time, let me welcome Mark Hughes to give us the overview. Mark.
Hi, thank you, Andrew. Can you see me okay?
We can see you okay.
Okay, I'm going to attempt to share my screen.
Just waiting for your screen now, Mark. There we are. Yep.
You can see my screen, yes?
All good. Far away.
Great, thank you very much. Well, thanks very much for the opportunity today to speak to you about some specific applications of Chemours A2L solutions, very low GWP. I'm Mark Hughes. I'm Business Development Manager EMEA with Chemours Thermal and Specialised Solutions, and I'm joined by a couple of colleagues today to talk in more detail about the path to net zero, low GWP A2L solutions for heat recovery and heat pumps. So I'm going to do a very brief introduction and then we'll get into the meat of it. The first presentation following me will be using our Option A2L products for heat recovery. It's basically adding that on to commercial refrigeration. That will be done by our technology manager in Europe, Samir Saab. And then following that, straight into that, there will be a presentation on heat pumps, on using our products in heat pumps to get the very best out of this technology, and that will be Pietro doing that, our regional marketing manager. So we only just changed from being Chemours Fluorochemicals into Thermal and Specialised Solutions, TSS as we call it for short. And it's just worth talking about that, particularly as we're talking about heat recovery and heat pumps, is that, you know, we've moved away from basically been just a refrigerant manufacturer to getting into the whole area of thermal management. So that includes embraces cooling as well as heating, but basically doing all of that using the minimum amount of energy. And obviously that's a key element when we're talking about net zero as we move towards the Green Deal in Europe and specifically the net zero by 2050 in the UK. So I'm not going to go into great detail here. This is our portfolio of products. The key ones really, if you like, are at the bottom of the screen there. These are the green ones. These are the sustainable HFO blends, A2L products, mildly flammable. You'll see here that the product XL20454C is shown twice, because basically it's pretty versatile. We can use it in the refrigeration side, and we'll talk today about how that also can be coupled with heat recovery in commercial, in retail refrigeration. But also it's also a useful product to get the best out of heat pumps as well, and can be used on that side. Another product which will be touched on as well is XL41454B, which tends to be used in larger equipments, but also has a place in the smaller heat pump applications as well. And again, Pietro will go into that in more detail. So, no presentation that I give will be, would be complete without my bubble charts. And this is really doing the, following on from the work was done on the wave study. And in fact, there's the next phase of that will be in Samir's presentation. But this was the initial work that was done, which basically shows that these new products, the XL products, XL40 and XL20, down in the bottom left-hand side, are the most favorable in terms of lowest emissions. And it just so happens that when you've got low emissions, you also get low life cycle costs, because the energy that you use is the most expensive part of the process of refrigeration. So you can see there the 454C down in the bottom left in the most favorable area. And indeed, if you do the comparisons, you see that the XL refrigerants have the largest emissions reduction versus the baseline, which today is 449A in XP40 in commercial refrigeration. So this is my final slide, and really, this is to really kick things off. The challenge of moving to net zero by 2050. It's all about emissions. It's all about total emissions and the energy performance of refrigeration systems. F-gases tended to focus us just on GWP, but that's only one factor, and a relatively small one nowadays as we get to GWPs below 300 or so. And the key, I think, for the UK and in terms of where we spend most of our emissions is in the heating of homes. And this is where harnessing the power of heat pump technology is one of the things that we need to do. That target there is a very tough one: 600,000 heat pumps per year by 2028. And then, if you do the sums, this is from the Heat Pump Association, which is part of the FETA, which I'm also working with. 90 million heat pumps will be needed by 2050 to get to that legislated net zero target. So we need to get on with it, and we can help with our technology. So that's it from me. I'll stop sharing, and I'll pass back to you, Andrew.
Thanks, Mark. I guess one of the issues we should get out of the way early doors is that when we refer to heat pumps, we're not just talking about a small domestic unit. I think one of the dangers, certainly with the way the government has been going, has been heat pump equals small domestic unit in their mind. But as we will hear in the course of this morning, there's a much wider application, and of course heat pumps, as the cooling side know, they can be very, very big indeed. And we should be trying to consider all of that this morning. One very important application is in the Low-GWP HFOs can offer is in heat recovery, as we're just about to hear. So let's welcome Samir Saab to tell us about the heat recovery options. Samir, take it away.
Yeah, thank you, Andrew. Can you see my screen well?
We can.
Perfect. So thank you everyone for joining us today. Today I will be talking about the use of Option XL20 in heat recovery applications for commercial refrigeration. As Mark was saying previously, the major part of the emissions today comes from the energy consumption. And on these charts, you can see on the left hand of the screen that 65% of global greenhouse emissions in the world is related to CO2 emissions, which means fossil fuel and industrial processes. And a major part of these is for electricity production. And if we look on the right hand of the screen, we can see this is more important in Europe, where it is more than 80% of the total greenhouse emissions in 2017, while HFCs and refrigerants are somewhere around 2.5% in Europe. And F-gas regulation today is aiming these 2.5%, which is a good start. But we should keep in mind that if you want to reduce global emissions, we should be reducing energy consumption and the GWP of the refrigerant, and not only focusing on the GWP value. From there, if we look at a supermarket store, and this is part of the WAVE study that Mark has talked about previously, we can see on this chart that the total emissions in a supermarket are related mainly to energy consumption, or what we call the indirect emissions. So you can see here the summary of the previous study, where we have compared 3 different cities in Sevilla, Leicester, and Helsinki, different architectures for refrigeration systems in a supermarket. And we can see here focusing only on CO2 technologies, flash gas bypass, or the best amelioration to the CO2 system, depending on each geographical area, compared to Option XL40 or XL20. And we can see that Option refrigerants can provide between 12 and 20% reduction in total emissions compared to CO2 in all the different climates we can see in Europe. But when we look only at this, we are putting aside one major CO2 or emissions production, which is the heating of a supermarket, because we don't have only cooling needs in a supermarket, we have heating needs as well. For that, we want to see in this upcoming presentation, is heat recovery a viable solution using HFO blends, or what the cost would be if we use these technologies. For that, we need to have a fair apple-to-apple comparison. How are we gonna tackle this problem? The best way for us was to search for the best partner who is capable of doing such work. And WAVE Refrigeration was the best partner for that, because they have started the previous study, and we have seen the quality of their work. And as you all know, WAVE Refrigeration is a well-established consultancy based in the UK. They have worked on the different international and UK retail chains. And they have been gathering a lot of information from the market, and they can apply their know-how to give us the best and more realistic results when they are doing their work. So let's move in this case to the assumptions that we have taken during this study. For a starter, we have picked up where we have left over the last time. So starting with the supermarket with a 2,300 square meters of a retail area, equipped with 160 kilowatts for refrigeration in medium temperature, 30 kilowatts in low temperature. We have taken only 2 geographical locations this time, Leicester and Sevilla. The baseline solution would be a supermarket equipped with a gas boiler, having an efficiency somewhere around 89%, which is the average of gas boiler efficiencies, or an independent air source heat pump to perform the heating of the spaces. And we have only considered space heating in this application. So we did not consider any needs for sanitary hot water or other heating needs. We have used the Opteon XL20 as a working fluid when it comes to air source heat pump. And when we are looking at Sevilla results, we have included as well air conditioning cost and emissions because the ambient temperature requires to have air conditioning needs, especially when the ambient temperature is above 30 degrees C. In this study, we have also looked at three different refrigerant to replace 404A. Here we are only presenting the results for CO2 and 454C or Opteon XL20. And you can see on the screen the assumptions regarding the emissions or the leak rates that were considered in this study. An important assumption also would be that all heat exchangers were assumed to be sized ideally, which means we did not do any compromise on the sizing of these heat exchangers for economical reasons. All the auxiliary like the pumps were not included, as they are common to all technologies as well. And last, you can see on the screen also the cost of the energy and the emissions for the production of the energy, either gas or electricity, for mainly two cities, so Leicester and Sevilla. And we've added also values for France, because France is known today to have one of the lowest emissions factor in Europe due to the use of nuclear, but we can imagine in the future the use of renewable energy would also reduce this emission factor. And it has also a low cost for electricity. So this might be interesting to look how these will look at these figures in the UK, for instance, or Sevilla. Now, if you want to consider heat recovery technologies for a supermarket, we have different possibilities. And we have considered three technologies here. The first one would be the compressor discharge desuperheating. This technology can only be used with Opteon XL20. So in a couple of words, you will see here a schema of the refrigeration system, or one part of the refrigeration system, refrigerant coming out of the compressor, high temperature, high pressure. After the oil separator, we will be having the refrigerant flowing through a brazed plate heat exchanger, where the energy will be recovered for heating and going through a water glycol system, performing the heating in different radiators within the supermarket. It will be here, in this case, in series before the condenser, and that's why we have this technology, in this case, the desuperheating at the compressor outlet. We have also different parameters we can adjust into this technology. Mainly would be the condensing temperature and pressure in order to adjust the water temperature, and finally having ambient air within the supermarket blown at 28 degrees C to perform the heating. The second technology would be the partial condensation. So it is quite similar to the previous one, but we can have a bypass on the different heat exchangers in order to maximize heat recovery on the brazed plate heat exchanger. In this case, this technology can be used for Opteon XL20 and also for CO2. This is what we call to water commonly when talking about heat recovery with CO2. And finally, we have a direct air handling unit condenser or gas cooler, recovering energy from refrigerant directly to the blown air within the supermarket. And in this case, also, we have a set of valves that will regulate or optimize the heat recovery while optimizing the condensing temperature or the gas cooler temperature. In total, there was more than 388 combinations that were considered. So that makes a lot of simulation that has been done by WAVE. Here we are trying to summarize the outcome of this work, which is a little bit difficult, as I said, because we have a lot of configurations. So there are too many ways to present the results as well. But since we are focusing today on emissions, and this is also the path for net zero is to reduce these emissions to the minimum, we have decided to sort these configurations. So each bar in this chart is one different configuration for heat recovery. The bars in blue are for Option XL20 or 454C. The bars in gray would be the ones for CO2 or R744. And we can see that the technologies providing the lowest emissions are the ones using Option XL20. And many of these technologies, or actually most of all of them, are having lower emissions compared to the baseline, which is here in red, using 404 and the gas boiler technology. But some of them might be more or less good compared to an air source heat pump as a baseline. In all scenarios, we also can see that we have energy or emissions reduction that can vary between 12 to 13%, going down to 70% of emission reduction compared to the baseline. And the most important thing that we can highlight here, that for both climates, in Leicester and in Sevilla, Option XL20 provides the lowest total emissions in these cases. But as we said, given this number of configurations, in order to simplify looking at these results furthermore, we will be focusing on the top configurations. For that, we need to set a target, which we have considered to be 40% lower emissions compared to a 404 system with an air source heat pump. And that's the green bar you can see here, or the green line for Leicester. And the line is set at minus 35% for Sevilla. In order to not to have a lot of information on the screen, the different configurations were given an ID number from 1 to 9. And as you can see here, we have sorted now the different technologies by their life cycle cost, so the LCC over 10 years. And we can see now that the technologies giving the lowest life cycle cost are not the same ones providing the lowest emissions. So once more, we are facing a dilemma. Which technology can we use and which is the best technology? Nevertheless, as you can see here once more, for Leicester, we can see that 7 out of the 9 top 10 technologies are using XL20. And for Sevilla, 6 out of the top 6 technologies also are using XL20. So to look at this in the most easy way, we need to use the total CO2 equivalent abatement cost. So maybe you have seen this formula before. It is in reality a combination between life cycle cost and emissions, and it will represent the best technology you will have for a given cost in order to have the minimum reduction in emissions. So it is not showing the lowest emissions, it's not showing the lowest cycle cost, it is showing which is the best you can get out of your money. And when we have abatement costs on the negative values, it means we are gaining money, we are doing some cost reduction compared to the baseline. At the same time, we are reducing the emissions. So as you can see here on the screen, the top 8 technologies in the UK are reducing the cost while reducing the emissions. And all of the technologies in Spain also are reducing the cost while reducing the emissions. And if we look also closely, we can see here that technology number one, that we will state what it is later on, and in the UK and in Sevilla is actually one of the best ones in order to achieve the lowest abatement cost. Now we have also said what will happen if we have a low emission factor. So we are producing our electricity in a green way. Would this change the outcome of the study? Or if the electricity will cost less, which we doubt a little bit, but if it is the case, what will be the impact also on these study? So if we take its decision today, will it be different or will the impact be different tomorrow if the energy cost is different and the energy factor emission is different? For that, we have applied the emission factor, the ones from France, and we can see that in blue here, the top 3 technologies will remain the ones using XL20. And they will continue to provide the lowest life cycle cost. As you can see it here, it is the lowest life cycle cost. So XL20, in conclusion, today is a good technology to perform heat recovery while reducing up to 70% compared to a 404 system using a gas boiler. Even though CapEx might seem higher at first, but the life cycle cost would be reduced by down to 15% compared to technologies using 404 with a gas boiler. In both hot and moderate climates, XL20 offers the lowest 10-year life cycle cost, so down to 11% lower compared to CO2 option. And it will offer also the lowest 10-year emission, in average or at minimum 13% lower compared to CO2 option. The best technology we have seen out of this study was the partial condensation technology using XL20 with a minimum head pressure equivalent at a 25 degrees C ambient temperature. And finally, Option XL20 can be incorporated into heat recovery strategy and is capable of outperforming other low GWP options like CO2. Thank you for your attention. And if you have any questions, do not hesitate to plug them in the Q&A section of the screen, and I will be glad to answer these at the end of this presentation.
Thank you, Sama. Now, normally we'd wait till the panel session for the questions, but there's a couple of specific ones. It's probably good just to tackle them now while they're fresh in your mind and the audience's mind. The first one is, does the 10-year life cycle calculation take into account the safety considerations and the cost of those that will be required for lower flammability? Do we know?
Indeed, as we said, this work was done by Wave Refrigeration, and maybe you have seen some of the communications they have done. They have already worked on several A2L refrigerant systems, and they have now the habit of including in their CapEx the small increase of cost when it comes to use of A2Ls. Today, it is a very limited increase of cost due to the use maybe of some leak detectors and safety measures like shut-off valves or safety alarms. And this is not big compared to the global CapEx of a refrigeration system, including, of course, now the heat recovery system. So it does include it, even though it is very limited.
Excellent, thank you. Now, the second question, also on the calculations, might be more complicated, and that is, what exactly is factored in with the indirect emissions calculation for, I guess, things like the electricity generation? How much drilling down is there when you're calculating indirect emissions?
So when we are calculating indirect emissions, we are looking at emission factors that are provided by usually the government of each country. And this is solely for electricity production. We are not taking into consideration the emissions linked to, for instance, the transportation of the system, the manufacturing of the system. We know that these will account for somewhere around 5% in the life cycle emission or the global emissions. So here, when we are looking at direct and indirect emissions, in other terms, we can call it the TEWI, or the total equivalent warming impact.
Excellent. Thank you, Samo. We'll come back. We've got some more heat recovery questions coming up later, but we will now pass on to your colleague, Pietro Sonza, who will be telling us about heat pumps in all their various forms, I'm sure. So Pietro, it's over to you.
Thank you, Andrew, and good morning, everybody. I'm attempting to share my screen. Andrew, could you please confirm when you start seeing I'm sharing?
We are now sharing, Pietro.
Perfect. Thank you very much. So the following short presentation has the intent of providing a perspective on heat pumps in the present decarbonization context, with a little overview on the key applications, the refrigerant technologies, and present and future options. Today, we all know that one of the major contributors to global warming and CO2 emissions are fossil fuel-based equipment related to heating applications. This is one reason why legal requirements on energy efficiency and CO2 emissions reductions are leading the way to more environmentally friendly and more energy efficient heating solutions. And heat pumps actually play a key role thanks to their inherent energy efficiency performance, and also thanks to their capability to replace energy inefficient fossil fuel-based equipment like gas boiler or gas burners, and also contributing this way to the continental decarbonization objectives. In 2018, the European Environmental Agency, the EEA, provided an overview on greenhouse gas emissions projections for the period 1990-2050. This graph is actually taken from that report and shows that the 2020 reduction target was minus 20% compared to 1990 figures. And also that 2030 reduction target is 40% versus 1990 figures. The report indicates that 2050 CO2 emissions should be reduced by 80% to 95% versus 1990 baseline. And in order to reach these targets, which are pretty ambitious at a European scale and concerning the UK particularly, additional measures are requested on top of the existing ones. This was one of the drivers for heat pumps to be identified as a key enabler to reduce CO2 emissions and for replacing fossil fuel boilers and electric heater systems. So when we look at heat pumps from a broad perspective, they are all based on a well-established technology. The broadly adopted vapor compressor cycle that Samer has also explained for the commercial refrigeration systems, for industrial refrigeration, transport refrigeration, is well-known technology. Several millions have been installed at households and industrial premises across Europe. And many world leader equipment manufacturers are actually European companies, not to mention the vast installation market expected to grow rapidly in the UK in the coming years. Now, three main applications can be identified. Residential, and these broadly applies both to new builds and house renovation, district heating, and commercial industrial applications. In all these applications, anyhow, heat pumps can be used for heating, cooling, and producing hot water, which makes them an extremely green and useful technology, as according to the European Partnership for Energy and the Environment, 40% of the European energy consumption comes from building. And 80% of that is consumed actually precisely for heating, cooling, and hot water production. So this is a fast-growing market. And while over 16 million heat pumps have been already installed in Europe, Mark also mentioned numbers of experiences across different nations. So far, according to the European heat pump associations, projections are for a very steep growth over the next coming years. From an end user perspective, three main technologies exist today. Air-to-air, where calories are simply exchanging between the ambient air and the air in the building. This is represented by the blue bars in the chart. Sorry, the orange bars in the chart. And the blue bars show the air-to-water application. This is a technology where the exchange is operated between the ambient air and a conveying fluid. And then there is a third technology represented in gray in the chart. These are the ground source, where calories are extracted from the ground through serpentines carrying a heat conveying fluid and then inside of a building. This represents a minority of the total European volumes, but it is particularly interesting for low ambient climates. This is the reason why it's so successful, for example, in Scandinavian countries or in Northern European countries, wherever an higher effectiveness and efficiency of the machine is needed, and stability throughout the seasonal fluctuations is also required. Ground source, among other things, contributed to high adoption in some specific countries. Norway is an example, for example. But no matter the heat source, heat pumps are ultimately electric machines with at the core of the system an electric compressor, hydraulic and electronic components, and they use the thermodynamic properties of an appropriate refrigerant to allow to move calories from one point to another. And this happens in a very energy efficient way. Actually, the performance of these machines is very simply determined by how much thermal energy can be exchanged in between one of the sources we mentioned, being that air or ground, versus the electric energy needed to operate that system. This coefficient, which is called the seasonal coefficient of performance, or SCOP, is compared to other technologies. When compared to other technologies, actually, is very high, very often over 3.5, and in some cases, depending on the climate conditions, it can reach higher numbers. And this is what makes this technology so attractive and also so green. Now, for this green magic to happen, a carrying fluid needs to exist. And this fluid has to offer, first of all, the requested thermodynamic properties. The industry, if we look from an historical perspective, the sector is coming from a multi-decade convergence towards a narrow range of refrigerant fluids. Like many other applications based on vapor compression, this technology developed around refrigerants like R22 and hydrochlorofluorocarbon, and then evolved adapting to hydrofluorocarbons, HFCs solutions, mainly for 10A, which is estimated presently at covering about 75% of the installed fleet, and 407C or 134A estimated to jointly cover the remaining quarter of the total market from a European perspective. When the global warming potential of the HFCs technologies was identified, the industry then started searching for new lower GWP alternatives for heat pump applications. And what happened then is that a selection process started being operated by industry. So different alternatives, which are listed here in the bottom left graph, in order of global warming potential starting from the top, show the different advantages and drawbacks, which you can find in the bottom right box. And the industry identified for each solution a certain number of features and drawbacks, and tried to cope with different technology advancement in heat pumps. So from the bottom, if we read the graph, we can find the three solutions that we mentioned, which are presently enabling basically this market to operate. And going up, we can find the different alternatives which have been tested over the years. Some of the remarkably clean solutions, like water, for example, simply cannot satisfy the requirements. Other less clean solutions, like ammonia, present too high drawbacks to be adopted. Toxicity, just to mention one, CO2 shows thermodynamic performance, which are not necessarily compatible with the price effectiveness of this kind of applications. and this is due to the low thermodynamic performance of the refrigerant, which makes it less suitable for a broad adoption in heat pumps. Although this is a very good solution for larger commercial refrigeration systems, for example. So over the years, from this selection process, one midterm solution, the R32, and two long-term 0-DP and very low GWP technologies emerged. One being 454C, or Option XL20, which is a hydrofluoroolefin blend, and one hydrocarbon, which is a R290 or propane. Among the criteria and the trends leading to this selection were energy performance, safety, and also ease of maintenance and installation, which is a key parameter for this technology to be broadly adopted, safely installed, and practically succeed on the market. R290 offers excellent thermodynamic performance. It's a very good refrigerant and a very good material compatibility as well. Its flammability behavior makes safety major concerns in a specific application. This, for example, precludes its adoption for indoor applications where the refrigerant charge exceeds a few hundred grams, which is very common in house renovation, for example. And anyway, this limitation imposes specific safety measures along the entire value chain, from component selection, which in most cases requires a specific design to prevent sparks, for example, to design, manufacturing, installation, operation, and maintenance in the end. So this is one of the reasons why a single solution does not fit all the applications. And in essence, the two main conclusions from decades of evolution and from experience built with heat pump applications are that first, energy performance, but also safety are key requirements. And second, that the industry is converging to two long-term sustainable solutions presently. Now, safety standards are obviously regulating heat pumps, both from the equipment manufacturing perspective and from the installation perspective. The latter is very well covered by one relevant standard, ISO 5149, and the correspective EN 378, and it's setting the charge size limits depending on minimum room size in different application scenarios, whether it is a floor installation, window, wall, depending on the configuration of the room, etc. So this chart shows, in essence, the regulatory requirements for A2L refrigerants and A3 refrigerants in the kind of applications that we have explained so far, and also the limitations of refrigerants, which, as we said, carry excellent thermodynamic properties, but have, on the other side, safety concerns, while A2Ls can cover that from another perspective. So although the thermodynamic properties are not equal to those of propane, they carry this mildly flammability behavior, which is making them safer and allowed to be used in larger quantities, larger charges for different applications. Now, say that we already mentioned that the coefficient of performance, the COP, and efficiency are two key parameters for the success of this technology. This chart shows a theoretical capacity and COP comparison for different non-hydrocarbon refrigerants, which exist on the market, and that we compared with 410A baseline, since this has been, as we mentioned, one of the references of the market, and it is still practically making 3/4 of the existing fleet operating today. This is outlining how different refrigerant choices are leading to quite different performance levels. And it's also outlining like refrigerant options like 454C show very interesting outcomes in all configurations. Another interesting aspect that the industry has been looking at, and we have been very interested at the beginning as Chemours, is the capability of dropping in new refrigerants into existing applications. When something new comes on the market, everybody is asking, shall I design a new equipment or can I use it with my existing equipment? Now, several drop-in tests exist and were carried out in different shapes. but very often with mixed results. In fact, a simple drop-in in existing systems is not leading to satisfactory outcomes. And this is due to the fact that the optimization efforts are required in order to optimize the unit based on the thermodynamic properties of the refrigerant. The graph shows relevant gaps, for example, in between expected performance, projected and theoretically calculated, and the tested outcome in a number of scenarios. There are also other parameters intersecting these problematic. One is, for example, the intelligence, the growing intelligence on board of modern heat pumps. In some cases, they have learning capabilities. The adaptation of the refrigerant is passing through algorithms that the controller is imposing to the machine. And unless components and system and the software are designed for a specific thermodynamic property of the refrigerant, it's difficult to achieve the best that can be achieved with a specific refrigerant. So in essence, equipment design optimization is a key requirement today to achieve optimum efficiency potential and to enable this technology to cover its green role that we have mentioned so far. As an example, among the market references having already adopted Opteon XL20 454C refrigerant is Stiebel-Eltron or other manufacturers. What is interesting, I found in Stiebel-Eltron development is that they came out with two great achievements. One is that the high flow temperature of their products is now allowing, thanks to the thermodynamic properties of the Opteon XL20, water temperatures of 75 degrees Celsius, which is a remarkable achievement, and it is one key differentiating element in several markets. So higher temperature for the hot water. And the other quite fantastic achievement is that through an optimization of the system around the thermodynamic properties of 454C, it was possible to achieve a 15% COP improvement versus the baseline, and by baseline I mean the previous fleet manufactured by the same manufacturer, which was based on 14A. And this is remarkable because at the same time they could achieve the implementation of a very low GWP solution in a safety manner, and with both performance enhancement and end user benefit improvements. So which refrigerant is most suitable for heat pumps application depends on several factors, such as thermodynamic performance, maximum safe charge size allowed, local economic and regulatory situation, the specific application, whether it's indoor or outdoor, which kind of heat source and cooling exchange is operated, installation conditions, as well as other factors. There is no single alternative that can replace F-gases in all heat pump applications today. We have been covering domestic application, but like Andrew outlined, there are several other segments where heat pumps are becoming relevant technologies and key enablers for more environmentally friendly solutions. And there's no single magic and single solution that can cover them all. That said, HFOs performs, and particularly Opteon XL20 and Opteon XL41, are long-term sustainable solutions that performs very well in many of these applications, particularly in the residential heat pumps. So just to wrap up, in summary, heat pumps are critical to the success of the European Green Deal because they provide a unique advantage to enable decarbonization and energy economies. In order to accomplish that, different refrigerant solutions need to coexist to address the key requirements of energy efficiency and safety. And HFO can satisfy that requirement by offering competitive advantages, both in terms of safety and efficiency. Also, circular economy considerations are critical to this business segment, as particular measures of addressing equipment end of life, for example, end of life management, but also broader installation certification programs are definitely needed. We are dealing here with either highly flammable or mildly flammable refrigerants, and we will be dealing more and more in the future. So certification, installation skills, and safety are key requirements. And last but not least, we need the regulatory stability because uncertainties risk to delay the deployment of this green technology. So in conclusion, like for all other applications, the options to unleash, allowing to unleash the green progress with heat pumps should be evaluated based on several criteria. The design of the unit is one of them, and they must all be science-based, based on objective consideration of all the parameters we mentioned. I thank you very much for your attention. I'm more than happy to answer your question during the Q&A session, and I give back the line to Andrew.
Thank you, Pietro. So now we come to the point where we have the Q&A, the question that goes into question time. So we're going to invite back our three speakers. Now, when we come to this session, we inevitably have, particularly in the subject that we're talking about, inevitably we have a wide range of issues to consider. And we've got some questions on the line, we've got some specific ones, and we've got some general ones. The skill of the chair will be to try and make this flow, but I'm just putting this out there. We may have to tackle some specific ones and then move on to general ones and vice versa. But please do keep your questions coming in. And I will kick things off with a general question, which is the reference to life cycle emissions. So CIBSE have said that 80% of the emissions for heat pumps are related to leakage. So is leakage actually not the bigger issue than energy in some respects? Who's going to tackle that one?
I'm happy to give a first answer,
yeah,
and then maybe Samuel
far away
complement on that. It is not, to provide a very short answer. We have run several studies, independent bodies, and with high credibility in Europe have also done several studies. The outcome is always converging on the fact that the direct leakage is important to address, is something we have to tackle, but it is not the major source of environmental issues. The environmental impact, particularly in terms of global warming potential, is coming from the system emission, which, as Sam explained, is encompassing a broad spectrum of considerations, but it is mainly driven by the efficiency of the system itself. So highly tight or environmental friendly fluid carrying equipment are not necessarily the most efficient. And the balance must be done at the end of the day on the entire life cycle of the system and the entire spectrum of emissions that are coming from the system.
I think it's fair to say that some people get very excited about GWP, some people outside of the industry. And I think part of our role is to, as I guess you guys have done, is to keep pointing people back to the importance of energy. Both are important, and as you say, Pietro, you know, keeping the refrigerant in should be the key goal, the fundamental to begin with, and particularly when we're moving across, perhaps with heat pumps, to people who are moving into the sector, that becomes even more important to understand. Another question that has come in, and I guess we should tackle this early. Pietro, again, you did touch on it, but why aren't we using R290 in all small AC systems?
Yeah,
Mark, you going to answer that? Mark was half about to answer, Pietro.
Sure.
I can tell from experience when he's about to jump in now.
Please, Mark, and you are on mute.
Yeah, get off mute.
Actually, I was going to remain silent. No, I think Pietro's already said that R290 is one of the solutions that you have, but it doesn't cover everything. I mean, particularly as you go to larger charge sizes, you know, if you look at in commercial applications, for instance, the effectiveness of propane actually drops off. That's a well-studied factor. At the smaller end, sure. You know, if you go into the smaller charge sizes, you know, like you might have in your domestic refrigerator, that's obviously been very very clearly demonstrated to be, to have a good level of safety. I think as you move into higher charge sizes, you start to get into more risky areas, and of course, then it really depends on, the skill of your contractor, and you're very in the hands of, contractors who, still require upskilling. The point about the A2Ls is that they're actually easier to handle, and the larger charge sizes can be put in there much more safely with all the risk assessments that are provided with that equipment. So I think, there is no one size fits all. To say that hydrocarbons can be used for all applications is facile, and there's actually a lot more study behind that, and we need to ensure that we keep our industry, our contractors safe, and indeed the end user safe. Those must be our primary focus, as was brought out in Pietro's presentation.
And maybe if I can add on that, Mark, that was very, very good summary. From a more technical perspective, there are key parameters determining the risk of flammability. One key parameter is the minimum ignition energy, MNI. So the propane specifically has an MIE of just 0.25 millijoule, and most electrical components can produce this energy. So like I mentioned, there is an effort of design that can cope with that. But when you compare that with A2Ls, which have values over 2,000 times higher, around 300 millijoules in some of the blends we mentioned today, you can understand that in case of an accident, the severity of the accident is determined by many other factors then, such as the burning velocity and the combustion energy. So, like Mark said, for small charges, this is a fantastic refrigerant. Objectively, the thermodynamic properties of propane are very, very good. But when you increase the charge, this severity factor becomes much higher. And if you look at the charge sizes that we have in the example that Mark mentioned, the Frigo at home, that is consistently lower than many of the applications in heat pumps or air conditioning, back to the question from the audience. And this has to be addressed both at a standardization level, where it is, with the limitations in maximum charge size, but also in terms of installation, safety, choice of the end user. And that is what probably is limiting a broader adoption of hydrocarbons for this specific application.
Okay, thank you. I guess it's a good point to go on to address. I guess it's a residual concern, because some people won't be familiar with the concept of lower flammability A2Ls, and they will just hear the word flammability. So it's probably worth one of you sort of setting out, in practice, what does this mean if we have these refrigerants in our heat pump, in terms of design and risk assessment, I guess. What's Mark said, it's a relatively straightforward process, but let's spell that out for the audience. One of you. Who's going to take it on?
Well, let me, obviously, from a UK-centric point of view, working with the trade associations, it's very clear, and indeed the Heat Pump Association, the manufacturers within that, part of FITA, there's a lot of guidance that's coming out now around the handling of these products. And actually, as people get more involved in that, they see that actually what's the fuss about, I think is one of the terms that was used. Not to say that this is to be ignored, because it's something that has to be looked at. Effectively, I think I've said this many times before, that all the refrigerants we're going to be using in years to come are going to be somewhat explosive, toxic or flammable to some degree. And you pick the least, ones with the lowest issues, and if you have mild flammability or low flammability, then that actually does reduce that quite significantly. So there's a lot of work out there from the manufacturers themselves to make the equipment intrinsically safe, and the key then is, how do you put them in, how do you install them, where do you position them? And again, that guidance, particularly from the OEMs, is getting has already been produced and is very strong, you know, from the majors. And you know, the likes of Stiebel, Eltron, who are bringing in the XL20 units. You know, there's a lot of information that's available to installers about how they are to be positioned. But you know, it's only just a slight step up from doing HFCs, because you know, you have a very minimal risk because of the difficulty of making them ignite, and obviously if you keep the stuff inside and make sure they don't leak, then you're never going to reach that situation. So it's always about avoiding a flammable atmosphere. But if you did get one, what have you got out there that can cause ignition? It's actually that's why I said it was straightforward. The design of the equipment helps with that, because you can produce them without ignition energies that would, and there's a standard there now, 60335 2-40, which covers that in great detail, an equipment standard which trumps everything else. So you know, we're in good shape as far as industry guidance is concerned.
Okay, so moving on from that, you mentioned Stiebel Eltron. Are other heat pump manufacturers now looking at using the very low GWP refrigerant? What stage are we at? Is this something that we can go and look at now, or are we talking a year hence or 2 years? Yeah, where are we at with heat pumps and the very low GWP?
Well, indeed, the solution is presently being adopted by several European manufacturers. As we know, heat pumps is a very European thing. In North America, for example, this is seen from a completely different angle. Mm-hmm. So it was born in Europe, basically. It is now broadening, being adopted in several countries. The work towards the adoption of low GWP solutions started several years ago. Manufacturers that you can see now on the market have already started walking that path 2-3 years ago with the optimization design effort I was mentioning during the presentation. There are several names who have already publicly endorsed, and we are aware of many others who are at the edge of releasing public announcements and extended the product range adoption for low GWP solutions. And others have also endorsed hydrocarbons, in all fairness. So this is why I was mentioning the industry is converging towards these two long-term sustainable solutions. And most of the leading equipment manufacturers have already contacted the refrigerant manufacturers years ago, starting doing the test. There has been a component approval process, which has taken years as well, because you need a compressor to be available for building a heat pump based on a new refrigerant, new electronics, new hydraulics, exchangers, etc. And this process, like I said, started some time ago, is now full speed, and we expect 2021 to be a key pivotal year for the heat pumps. I was showing the heat pump association numbers in terms of projections, and then when you look at the different countries, particularly the UK, there is a steep growth expected in the coming years. And this is thanks to the work which has been done in the past years and the fact that these solutions are now available broadly on the market.
What do you think will move the market or move things more quickly? I guess it's a question for Mark, isn't it? What's the view on regulations and heat pumps and lower GWP from your perspective?
Well, of course, the overriding thing is F-gas, and now, of course, it's GB F-gas. It'd be nice if it was sort of UK F-gas.
G-gas, we're trying to coin it now, aren't we?
G-gas, is that okay? Fair enough. Whatever it is, that is the reduction in quota, and within the UK, that looks like it's going to bite a little bit faster than the rest of Europe, because we don't appear to have the stuff coming in through legal means or quota busting. But I mean, that's to be seen. But we believe that within the next year we will see a level of tightness that really then focuses the minds of those who are bringing equipment into the country. For instance, a lot of the heat pumps are manufactured outside. When you bring them into the UK, they need to have quota if they're pre-charged. So that's another cost that comes on. The lower the GWP of the product that's inside them, the lower the cost. Now that applies obviously to things like propane as well, for the smaller bits of kit. But something like an XL20 with a GWP at 148 is actually eats very, very little quota, and I would love to be able to provide that quota rather than having to stick 410A or even 32 into stuff, which eats much more quota. So it's about how quickly we eat the quota. I think that's the pressure. There are some bans that have come in, but I don't think those really are going to push the thing any faster. Certainly in the UK. Mobile air conditioning and dehumidifiers that use heat pump technology have already been, have already had bans in place, and the likes of people like Dantherm already have using XL20 in their mobile dehumidifiers. So, that did have an effect, but I think the biggest effect will be the phase down and the way that the UK is handling that, and so far so good from a F-gas working point of view.
Very comprehensive answer, Mark. It might be slightly outside of the scope of what we're talking about today, because we're sort of thinking about the upstream considerations. But there's a question come in which is around, what does the panel think about the need for skills when it comes to upskilling specifically the heating industry, who may not be so familiar with refrigerant, and the whys and wherefores of lower flammability, but also refrigerant handling in general. I guess we're inviting you to say we need some leadership from the government on incentivizing skills as much as anything else. But I guess it also applies to design as much as it does to installation, doesn't it? What do you think about that? That's a Mark question. Sorry, everybody else.
I sorry.
That was almost built for Mark.
Yeah, but it's one that, it just occupies my time, within FITA, within ACRIB, we're lobbying the government very strongly. We think the F-gas review shouldn't just include F-gases. It should be all alternatives, to the higher GWP gases, and therefore, there should be mandatory training within that for any refrigerant gas, anything that could get out of the system or could cause harm. So I think, I know government's listening, and in the past they've been reluctant to do it because they saw it as sort of gold plating, already EU legislation. But of course now we have UK F-gas. You have the ability to put that in there and really help with that transition. There's a lot of people that need to be trained, but to just bring the bar up, it doesn't need to be brought up, massively. It's just enough to ensure that we have, there's a lot of engineers out there working on gas boilers, heating engineers that I reckon could be easily upskilled if there was clarity about what they needed, and that's starting to be provided by, the associations. But I think we need the government behind it, and we're lobbying like mad to try and get that done. There's not a week goes by without some publication or paper, and behind the scenes, we are consulting with government as stakeholders to try and move that forward. So it's a big area, and I know it's something, in your own magazine, Andrew, that you're banging the drum about, which is great.
Well, it's clearly important, as you referred to earlier, that refrigerants are changing. There's no two ways about it from the A1s that we were used to, and so that will require an element of training, and for that to happen, we need some drive, and we'd like to think that with all the talk about training from the government, that we'd get something from them. But that depends on all you out in the audience writing to your MPs and saying, what are you doing about refrigerant training and heat pumps? It's all well talking about heat pumps, but we need to provide the infrastructure. Anyway, I'll get off my soapbox. That's not my role here. I'm very conscious Sam has hardly had a word, but there's a couple of things at least here for you, Sama. So first of all, I want to introduce a general element, and that is, we talked about heat recovery in particularly in supermarkets. Are the end users, in your view, are they fully aware of the potential of reusing the heat? Are we halfway there? There are a lot of work to do. What's the feeling? Because we hear about heat recovery a reasonable amount, but then again, I'm pretty sure there are stores there that have no facilities for reusing heat. So what's the potential, Sama?
The the potential is huge, Andrew. Today, we see little people using this technology, mainly due to one factor, which is the increased capex when we are doing the investment to install our refrigeration system. When we look at the first investment we are putting into a supermarket, we might see this frightening that we have an increased cost. But as we have seen in the presentation we have provided, that this can be overcome in the life cycle cost over 10 years. And even if we consider that this refrigeration system might live longer than this, we will have sustainable and substantial economy done with the heat recovery system. So we shouldn't only be focusing on the capex of a system. We should be looking how much the system will cost us over 10 or 15 years. And that's very important to increase the use of heat recovery that today is still little known, to my opinion.
So plenty of scope out there. Now I've got a specific question to follow up, so I'm going to read it carefully. And again, for those who are not familiar with RAC webinars, as I get older, I have a bigger screen to my right. It makes me look like I go a bit cross-eyed, but I'm reading specific questions and making sure I get them right. So Salman, this is the question. The heat recovery calculations that you used, what percentage were you factor in the available heat from the cooling load? Do you consider forced load heating in that? And how do you intend to make up the remaining heating capacity which will be required?
Okay, so if I understand the question correctly, in the systems we have considered today, when we are in a steady state, which means we are in winter, the supermarket inside is at 20 degrees, outside it is -2, for instance, we have enough heat provided by the refrigeration system to have the heating of the supermarket. Nevertheless, when we are at the beginning of the heating season, which means we are somewhere maybe in October or November, we didn't have the heating system on, and now we want to put the system on. So the temperature inside might be a little bit lower than the average or the aimed temperature of 20 degrees. So we need to heat up the supermarket. So it is a startup. Here we do not have enough heat generated by the refrigeration system. For that, Wave Technology has provided several technologies. So it's starting with maybe an additional boiler that can be used only for these startups, or having an external evaporator. So we are using the refrigeration system as a heat pump to drain the heat out of the ambient air and providing it to the supermarket. Both would have an added investment, and this has been taken into consideration in the calculations. And these are some of the configurations that we did not show because otherwise it would have been very complex to explain everything. Nevertheless, we did not, on a steady state, we are not using a false cooling, or we are not increasing in a non-needed way the refrigeration needs. Maybe for startup time, we might need this, yes.
Thank you.
Of course.
There's always the tricky bit with a specific question that I get it right, and you've answered it very well, so well done. Now time to throw in an observation. This is always just to, we don't just have questions, we have people making observations. So this is back to heat pumps. So the Heat Pump Association is close to launching a course to reskill existing heating engineers to enable them to install heat pumps. So this refers to the skills discussion. It's focused on monoblock HPs at the moment because they are sealed units and hence the likelihood of leakage is minimal. But we are rest assured the HPA is working closely with government to promote both heat pumps and the training to go with them. So that's reassuring. Thank you to Martin at FITA for that. I think we want to go on. You know what we haven't talked about yet, really, and that's big old heat pumps. It's a mission of mine whenever we talk about heat pumps over on the HMV News side is to remind people that heat pumps don't end at the ones that go in your house. There's some considerably bigger ones, and I believe there's quite a bit of work going on amongst the larger heat pump chiller manufacturers with the very low GWP refrigerants. Who's going to give us a few sentences on what's going on with the big units? Is that one for Mark or Pietro?
Well, I'll start things off, but I know the guys, the guys on the call have been working behind the scenes with, for some years with some of the bin manufacturers. But I think basically, I don't think a week goes by without there being a public, an announcement by one of the big manufacturers, whether it be Train, Carrier, Johnson Controls, or or many of the bespoke manufacturers in Italy, for instance. That's a very strong area for chiller manufacture. Mitsubishi, in that Mahitz, in that area, Hydronics, producing and now specifically producing heat pump technology. I think in the past, many of the chillers out there could potentially act in reverse and produce hot water or heating. But now, obviously, there's a specific label put on them, and they say, look, this is, 2-pipe, 4-pipe, whatever it might be. You can heat your hot water with this. You can do your heating of your space with that, at the same time as cooling other areas where there's excess heat, and you then take that heat out, and you're actually recycling that around. This is really, really good technology. The biggest area is 454B, which is the XL41, because basically these are like scroll chiller technology. 410A is the area, and as you say, they didn't want to go through massive redesign on this equipment. 32 has been chosen to use with that, but actually 454B has been shown to be the best and lowest GWP option to be 410A like, high pressure product and high capacity. So, you really need the guts on this one, which is where XL41 comes in. So, as I said, Train, I think they put in XL41 across their entire range. And again, that's been followed by Carrier and Johnson Controls. And the exciting thing for us as a global manufacturer is they've now chosen those products on a global basis. So as we start to go to Kigali, we've got the AIM Act in the US, it's looking very, very good for the introduction of those products. What we do need, though, obviously, whether it be locally or globally, is more regulatory coherence. I think Pietro put it, because we're doing all this work and all these guys are putting this stuff in, and there's still this thing saying, well, are these products sustainable in the long term? We believe they are. All the evidence points in that direction, but some of the legislation doesn't necessarily help us in that confidence. So for end users to make the choice, we believe that those big manufacturers now putting their label on, green 454B is going to help us, pushing in that direction. I don't know if the other guys have got anything to add, but in terms of the actual technology being used, but that's certainly from a market position.
Anything to add, gentlemen?
Oh, I think Mark made a pretty good summary on that one.
He is quite good at that these days, I think. We did address the long-term sustainability, so there are a couple of points and questions to throw in on that. The first one is, and I guess we should expect this to come up, so you probably got an answer. What's your position regarding TFAs? And if you'd like to spell them out for the audience, because I've only got the abbreviation here and I can't remember.
Sure. I can happily do that. TFA is actually the acronym for trifluoroacetic acid, which is a naturally occurring organic acid with a similar structure to acetic acid, actually vinegar. What is our position on that? Actually, our position is the position of the numerous studies which have been published so far on this subject. I know that this question is raised more frequently in the past coming months, because both there have been two events. First, some of the studies have been resurrected and reinterpreted by some of the parties in the industry, and there have been honestly quite a few, but new data which have been brought in. But basically, the science is studying the TFA since the 90s. This is today estimated as being 95% naturally occurring. It's coming from volcanic activities and it's emitted by deep sea vents. And over 200 million tons are estimated to be found in the oceans. Now, 5%, the remaining 5% is what we are talking about, is man-made. And this is coming from several sources of industrial activities. Manufacturing, as a TFA is used as an intermediate product in many processes, particularly chemical processes. To name one, the pharmaceutical production. Sewage treatment, for example, because TSA is demonstrated to be formed during the breakdown and ozonization of some effluents. Agriculture, which is considered to be one of the biggest sources of TFA today, where the breakdown of specific fertilizers and herbicides do generate TFA. And then refrigerants, which is more specifically where it is more specifically coming from the atmospheric decomposition of certain specific refrigerants. 134A is one of them. HFO 1234YF is another one. And the reason is that for HFO specifically, the molecule was designed to become unstable and to break down when exposed to the ultraviolet light in the stratosphere, in order to not impact on the global warming, in terms of global warming potential. And that disgregation creates a small amount of TFA, which is contributing to the basket I mentioned, which is from manufacturing, again, agriculture, sewage, and other industrial activities, which in turn is contributing. Today it's estimated that by several international panels in the proportion of 5% to the man-made contribution to the global TFA present in nature. Now, the big question which comes just after that is TFA harmful for the environment and for human health? And there have been, I would not like to take a stance on this, because there's already several committees, technical committees and official committees, which have been stating the impact, the known impact on conducted, and this is coming from studies conducted over the past 2 decades, the impact of TFA from man-made sources. So basically, this is a fair question, and it is a question we really take seriously. It has to be considered in the context of what refrigerants can bring in terms of contribution to the TFA, which again, 95% is estimated to be naturally occurring. And the real question is the refrigerant TFA contribution relevant to increase that? And there have been several projections, for example, over the next 30 years, considering the automotive fleet worldwide adopting HFO refrigerants, as 1234YF is de facto the standard in automotive air conditioning systems. And those projections, again, confirm the assessment which has been made by the several panels.
Thank you, Pietro. I think with this, in the world that we exist in, where there are sound bites and quick headlines, I think it's important sometimes to give comprehensive information out. And so, yeah, thank you for a comprehensive answer to what was actually a short question, but it's got a long answer, hasn't it? So I hope that is explanatory to everybody. Right, we're arriving at the point in our webinar where we've got our last few minutes, where I know time has, you can't believe it, can you? Time has flown by, but we have to come to the point where we start to round up. We've got about 5 minutes to go. So I want us to think about what messages we can leave with the audience. There's a question that's come in, which starts this off nicely, which is, how do we raise the profile of the heat pump technology with the key stakeholders who would be involved in their deployment? How do we coordinate at a national and local level to improve the take up and understanding of heat pumps? And as we've discussed, it starts at local and then moves out to global now with everything that's going on in Europe and the US. So, Mark, how do we start? Where do we start? What advice do we give?
Well, I think one of the things quite interesting is we've actually been approached by some of the national newspapers, the Sunday supplements and whatever, because their readership are getting interested in being green and having green heating and the fact that you basically put electricity back into the grid with the heat pump, because it got a COP of 3.5 or more. That's an attractive thing. The problem you've got is the cost of the equipment. It's coming down, but we need to have incentives. I believe in incentivization, and once you start to have incentives for the technology in place, then the whole thing just speeds up. It's a very, very clear position. I think in terms of having everything else available, then if that was the button that was pressed, the Heat Pump Association, through ANFITA, ACRIB, the organisations are all there trying to enable this, and I think we could probably get our act together pretty quickly. We've got to be able to manufacture the units. There's a lot of people out there manufacturing those units. We have them locally and I say and around the rest of Europe. What a fantastic injection of capital into that commerce with what's happening with the pandemic. We haven't mentioned COVID today, but obviously as we get, we talk about this green revolution, and there's some fantastic opportunities, but we need people to press the right buttons. I think we're now lobbying for government to start to press those buttons. The HPA are doing a fantastic job. They're producing papers all the time, and we fully support the activities that they're having, no matter which refrigerant is used.
I think that the tricky part, the challenge for us in conveying the information is to make sure, on the one hand, that the end user of the smaller heat pumps is comfortable, and is not swayed by scare stories about heat pumps in general, but then also that the wider industry, and in that I say that's all the way from HVAC to R in HVAC, is familiar with the opportunity, the various opportunities, and publicizing these kind of events are good in that it draws people's attention to the variety of opportunities. I mean, I'm taken with the big, what we call big heat pumps. Some people call big chillers, and I think we've got to work as an industry to make sure that people know that you can use the chiller, as a heat pump for heating as well. It's not just a question of putting a big cooling unit in. You can cover all your bases. And the energy equation, we're going on RAC, we've been talking about this quite a bit already. I think we're going to be talking about a lot more. It's that energy point. We shouldn't get swayed just by GWP, although it's important. It's about the energy use, isn't it? I'm encouraging you to say yes, it is. That's not my soapbox. I'm not doing a Jerry Springer ending. Because it's for you folk to give me, this is I don't know whether you've briefed your colleagues, Mark, but how we end all our webinars is we say, what one message could we give to the audience from each of you? So shall I start with Pietro? What's the one message that we want to take away today?
I think the one message I would remind here is that green pumps are a great enabler. And for the Green Deal, for the continental decarbonization objectives, for the UK specific decarbonization objectives, it's a fantastic technology. It's mature. There's several options on the market. It's something that we have to collectively help developing on the market. And there is these kind of events are the places where we can gather, we can exchange, and we can collectively push this technology forward.
Thank you. Sama, what have you to add?
I would add to what Pietro has said, this time from a commercial refrigeration point of view. And as you said, Andrew, we shouldn't be only focusing on GWP. GWP is one value, but we should be looking at the total emissions of a system and the impact on the resources we are putting into a system in order for it to operate correctly. How much the system will weigh, how we can recycle the system. And especially for heat recovery systems, we can see today that the combination of heat recovery with HFO blend refrigerant are the right way to go in order to reach net zero.
Thank you. So Mark, it falls to you to try and encapsulate your opinions in just 2 sentences.
I think probably I've said most of what I need to say. I just think we need to work together as an industry to to really meet the challenges of GB gas. As I say, try and steady the ship, continue to lobby, make sure there's a sensible policy out there, that joins up the refrigeration and air conditioning and heat pump side with the overall push to environmental compliance. So a lot of work to do, but I think we've got some ears. There's ears in government, listening. I think it's been positive so far. We just need to make sure that F-gas works.
I think thank you, Mark. Yes, I think the important thing is to keep talking, because the only way to outshout, if you like, the soundbite mentality, which is coming from some of the tabloids and others about what's wrong with heat pumps, is to shout louder with what's right with them, and it's these kind of events that are important. So thank you to our colleagues there at Chemours, to Pietro, to Sama, and to Mark. Thank you for the sponsorship of this event. Of course, it would be remiss of me not to say that these question time extra times, we can do these as often as people wish. So if you want to talk to us about sponsoring one, we can discuss all kinds of things as we dive deeper into the world of refrigerants in cooling and in heating, indeed. Thank you very much for listening. I think I'm right in saying that we'll put a recording up of this and that your slides will be available, gentlemen. Is that right? We're going to make them available? Yes, good thumbs up from Mark. So we'll have all that available to those on the audience, and then we'll be putting a story up, of course, on REC. And it just remains for me to thank you all for listening and enjoy the rest of the day. Of course, it's a UK majority audience, so can we say "Come on, England" tonight? I don't know. Perhaps we can. That'll probably be edited out of the recording for the Chemours audience. Thank you very much for listening, and see you soon. Goodbye.
Yes, thanks very much. Thank you, everybody.
Thank you.
Bye-bye.
Have a good day.
Cheers.
Goodbye.
Bye-bye.
Bye.